Welcome to the Deep Dive. We plunge in complex topics, pull out the key insights, basically help you get truly well-informed. Today, we're tackling the language of organic chemistry. Just imagine trying to decipher a blueprint for something incredibly intricate, like a molecule that's both beautiful and deadly. Think palytoxins, this natural compound, potentially has anti-cancer uses, but it's also, well, one of the most toxic things known. It's got, over 100 carbons, loads of other atoms all tangled up. Looking at the full structure, it's kind of mind-boggling. But a chemist sees something precise, elegant even. So the big question is, how do chemists possibly make sense of all that variety, that intricacy? How do they even start to draw, interpret, and talk about these structures? That's our mission today. We're aiming to give you a shortcut to understanding the fundamental language of organic chemistry, how we draw molecules, how we interpret them, how we communicate. And we're drawing heavily today from Chapter 2 of the big organic chemistry textbook by Clayden, Greeves, and Warren, really laying the groundwork for things like mechanistic reasoning and reaction pathways.
Exactly. Think of it as learning the essential handwriting of chemistry. If you don't get this foundation, the rest of organic chemistry just stays a mystery. It's like trying to build something complex without knowing what the parts even look like. So we're going to demystify it a bit for you today, show how these seemingly complex structures reveal their secrets through, well, just a few core principles. It's about spotting patterns, understanding the conventions chemists use every single day.
Okay, let's unpack that. So organic chemistry, at its heart, it's the study of carbon compounds, right?
Right. But it's almost never just carbon and hydrogen. Most organic compounds, the interesting ones anyway, they also contain oxygen, nitrogen, maybe sulfur, phosphorus, and those atoms are really where the action is, where the reactivity happens.
Oh, okay, so there's a key distinction then.
Absolutely. You've got the molecule skeleton, which is, the chains and rings of carbon and hydrogen. And then you have the functional groups. A really good example is amino acids. Think about glycine, alanine, phenylalanine. They have pretty different carbon skeletons, right? Some short chains, some have bulky rings.
Yeah, quite varied.
But chemically, they behave in very similar ways. They all dissolve in water. They're amphoteric, meaning they can act as an acid or a base, and they link up to form proteins.
And that similarity comes from?
It comes from their common functional groups. They all have an amino group, that's the NH2 bit, and a carboxylic acid group, the CO2H. So functional groups are exactly what they sound like. They're the specific groups of atoms that determine how a molecule functions chemically and biologically. The hydrocarbon framework, the skeleton, it's basically just the support structure.
Like our skeleton supports our organs.
Precisely. The framework holds the functional groups in place, lets them interact. It's the scaffold. The functional groups are the actual, working parts, the engine.
That's a really helpful analogy. And speaking of frameworks, how chemists actually draw these things on paper is like a whole language itself, isn't it?
Yeah.
Why is getting the drawing right so important, especially for, talking about reactions and transformations?
It's all about clarity and, honestly, efficiency, especially when you're trying to show how one molecule changes into another, like in a reaction pathway. So our first guideline is pretty basic. Draw chains of atoms as zigzags. You might see older diagrams with straight lines.
Yeah, I've seen those.
That was mostly for printing ease back in the day. But X-ray studies show carbon chains aren't straight. They adopt the zigzag arrangement because of the tetrahedral angle, about 109 degrees for single bonds. So our 2D drawings need to reflect that 3D reality, at least roughly. It gives a better feel for the molecule's actual shape.
Right, aiming for realism where it counts. But then you mentioned economy, leaving things out.
Exactly. We want realism but not clutter. So guideline 2 is miss out the H's attached to carbon atoms and the CH bonds unless you really need them.
How does that work?
Well, the principle is simple. We just assume any carbon atom that isn't showing 4 bonds is attached to the right number of hydrogens to make up 4 bonds. Showing every single hydrogen just clutters the diagram. It obscures the important bits, the functional groups.
Okay. And you even leave out the C for carbon sometimes.
Yep, that's guideline 3. Miss out the capital C's for carbon atoms unless necessary. Every kink in that zigzag line and every end of a line, we understand that represents a carbon atom.
Ah, I see. So the lines themselves represent the carbon chain.
Exactly. And this makes the functional groups, the non-carbon bits, stand out much more clearly. Now, of course, there are exceptions to those last 2 rules.
Okay.
If a carbon or a hydrogen is part of a functional group like the C in a CO2H group or the H in an aldehyde CHO group, or if it's directly involved in a reaction mechanism you're trying to show, then yeah, you should draw it in. It's all about clarity, you see. Not rigid rules. If it helps understanding, include it. If it just adds clutter, leave it out.
Got it. So it's finding that balance, realism, but keeping it clean and focused. What about showing the 3D aspect? You mentioned stereochemistry. How do you get that across on a flat page?
Right, that's crucial. We use special bonds. A bold, solid wedge, like a triangle pointing towards you, means that bond or group is coming out of the page towards you.
Okay, coming forward.
And a dashed or hashed bond looks like dashes receding, means that group is going away from you behind the plane of the page. Normal lines are just in the plane of the page.
Oh, wedges and dashes.
Yep, wedges and hashes. This lets us show the tetrahedral arrangement around carbon atoms, which is absolutely vital for understanding how molecules fit together, how enzymes recognize them, how they react in 3D space. It's fundamental for stereochemistry. So, to wrap up the drawing part, the goal is realistic, economical, and clear structures. This is genuinely the universal handwriting of chemistry. It's how chemists communicate visually every single day.
It really is like learning a secret code. I can definitely see why mastering this is critical before you can really understand reaction pathways or design a synthesis. Okay, now we know how to draw them. Let's dig into the actual building blocks. What kind of shapes does carbon form?
Carbon's ability to bond with itself is amazing. It leads to this incredible variety. The simplest structures are just chains. These can be short segments, like in polythene, you often see those drawn with wiggly lines at the ends to show the chain keeps going.
Right.
Or they can be incredibly long and complex, like in some natural products. There's an antibiotic called linear mycin. Its chain is so long, you practically have to wrap it around the page.
Wow. And chemists have shorthand for bits of these chains, don't they? Abbreviations?
Oh, definitely. For tidiness, we use standard abbreviations for common alkyl groups. Methyl is Me for a CH3 group. Ethyl is EAT for CH2CH3. Then PR for propyl, BUF for butyl.
So you might see MES instead of writing out CH3S.
Exactly.
Yeah.
Like in the amino acid methionine, it just cleans things up. And then there's the super useful wildcard R group.
R group.
Yeah, R just stands for any alkyl group, basically the rest of the carbon skeleton. It's incredibly handy because, like we said, reactivity often depends mostly on the functional group. So R lets us talk about a whole class of compounds without getting bogged down in the specifics of the skeleton. We can just say an alcohol, ROH, or an amino acid, where R is the variable side chain.
Makes sense. Generalizing. Okay, so beyond chains, there are rings. Kekulé and the snake biting its tail comes to mind for benzene.
Ah, the classic story. Whether it's true or not, the benzene ring is absolutely fundamental. It's everywhere: phenylalanine, aspirin, paracetamol, you name it.
And there's an abbreviation for that, too.
Yep. If you have a C6H5 benzene ring attached to something, we call it a phenyl group, abbreviated PH. And if it's any kind of substituted phenyl ring, we can use the wildcard aryl, or R.
Okay, VH and R.
But rings aren't just benzene. You get huge rings, like the 13-membered ring in muscone, which gives musk its smell, or fused rings, like in steroid hormones, testosterone, ostradiol complex frameworks with huge biological effects. And for simple rings, we just use the prefix cyclo, cyclopropane, a triangle, cyclobutane, a square, cyclohexane, a hexagon. You find these in all sorts of places, from insecticides to artificial sweeteners.
And it gets even more complex because these chains and rings can be branched, right?
Yes, absolutely. Hydrocarbon frameworks are often branched, and again, we have common names and abbreviations for these branched bits. Isopropyl, or IPR, looks like a Y shape.
Okay.
You find it in things like LDA, lithium disopropylamide, a really common strong base used in synthesis. Then there's isobutyl, IBU, which is an ibuprofen. Sec-butyl, SBU. Tert-butyl, TBU. The tert-butyl group is particularly bulky. You see it in antioxidants like BHT.
All these branches, does that affect how they react?
Hugely. And this brings us to a really crucial concept for understanding reactions for mechanistic reasoning. We classify carbon atoms as primary, secondary, or tertiary.
How does that work?
It's simple. It's just the number of other carbon atoms attached directly to the carbon you're looking at. A primary carbon, 1 degrees, is attached to one other carbon. Secondary, 2 degrees to 2 others. Tertiary, 3 degrees to 3 others. There's even quaternary, 4 degrees attached to 4.
And why is that important?
Think about access. A primary carbon is like being at the end of a quiet street. A tertiary carbon is like being in the middle of a busy, cluttered junction. This clutter, we call it steric hindrance, makes a big difference in how easily other molecules can get close enough to react with that carbon. It profoundly affects reactivity. Understanding this is fundamental if you're trying to predict how a reaction will go or design a drug molecule to fit into a specific biological target.
So the shape, the branching, it all feeds into the reactivity. But you said earlier the real heart of the reactivity lies with the functional groups.
That's right. The framework is the stage, but the functional groups are the actors. Think about ethane, just C2H6. It's pretty unreactive, right? It mainly just burns. But ethanol, C2H5OH, which just has that one extra oxygen atom in the hydroxyl group, the 8OH group, suddenly it reacts with acids, bases, oxidizing agents. It's much more chemically versatile.
All because of the OH group.
All because of the OH group. That hydroxyl group is the source of ethanol's reactivity. And other alcohols, no matter what their carbon skeleton, the R part, looks like, they tend to have similar chemical properties because they all have that OH group. So recognizing functional groups and knowing their general character is the absolute key to understanding and predicting organic reactions and pathways.
Okay, so let's maybe tour some of the important ones.
Good idea. Let's just focus on recognition and general character for now, not the deep reactivity details yet. First up, compounds with carbon-carbon multiple bonds. We have alkanes, which contain a CC double bond. They're called unsaturated, and they readily undergo addition reactions. Think of things like pine, that classic pine smell.
Okay, double bonds.
Then alkanes, which have a C triple bond. These are linear around the triple bond and generally even more reactive than alkanes. You find them in some complex natural products like certain anti-tumor agents.
Triple bonds, right.
Okay, next let's look at some common oxygen-containing groups. Alcohols, we've mentioned, have the hydroxyl group, ROH. They're often water-soluble, involved in hydrogen bonding. Think sugars like sucrose, full of OH groups. Then ethers with the structure R1OR2. They link two alkyl groups through an oxygen. Diethyl ether is a classic anesthetic. THF is a common solvent. Some natural toxins have incredibly complex structures made of multiple ether rings.
Got it. Alcohols and ethers.
Moving on to nitrogen-containing groups. Amines are NH2, or R2NH, R3N, contain the amino group. They're often basic, sometimes smelly, think decaying fish, but also vital components of amino acids, DNA bases, many drugs like amphetamine. Nitro compounds, RNO2, have the nitro group. This group can make molecules explosive, like TNT, but it's also found in some pharmaceuticals, like the sleeping pill nitrospam.
Okay, amines and nitro groups.
And we can't forget halogen-containing groups. Alcoholides are X, where X is a halogen fluorine, chlorine, bromine, or iodine. Their reactivity varies a lot depending on the halogen and the structure. Think PVC plastic, polyvinyl chloride, or methyl iodide, a common lab chemical.
Right, the halogens.
Okay, now for a really important class, carbonyl compounds. These all contain the CO group, the carbonyl group. This is probably one of the most versatile functional groups there is.
C double bond O.
Exactly. Within this family, you have aldehydes, general structure RCHO, and ketones, R1COR2. They're both reactive, often targets for nucleophiles. Acetaldehyde is formed when ethanol is oxidized in the liver. Acetone is a common ketone solvent. Chanel number 5 has an aldehyde. Raspberry flavor comes from a ketone. And a crucial drawing point here, always draw aldehydes as RCHO, showing the H attached to the C, never write RCOH.
Why not RCO?
Because RCOH implies the hydrogen is bonded to the oxygen, like in an alcohol, which is completely different. RCHO means the hydrogen is bonded to the carbonyl carbon. Totally different reactivity, different functional group family. It's a really important distinction for mechanisms.
Ah, okay, that makes sense. CHO, not COH.
Right. Now, related to carbonyls, we have carboxylic acids, RCO2H. They contain the carboxyl group. As the name suggests, they're acidic. Citric acid, malic acid, tartaric acid, and fruits. Those are all carboxylic acids. And derivatives of carboxylic acids include esters, R1CO2R2. They make up fats and oils, and many have characteristic fruity or floral smells. Think banana, rum, apple flavors. The difference between saturated and unsaturated fats relates to the R groups in these esters.
Esters, right, like in polyester fabrics too.
Well, related bonds, yes. Then ecanolyds, RCONH2, or with N-alkyl groups. These are incredibly important. Biologically, the peptide bond linking amino acids in proteins is an amide bond. Aspartame, the artificial sweetener, is related. Paracetamol is an amide. We also have nitriles or cyanides, RCN, with a carbon-nitrogen triple bond, and acyl chlorides, RCOCl, which are very reactive versions of carboxylic acids, mainly used as intermediates in the lab.
Wow, that's quite a list.
Yep.
It really shows how just combining C, H, ON, and halogens in different ways creates this huge diversity of chemical behavior.
It really does. And recognizing these groups is step 1. Step 2 is understanding how they interrelate.
Which brings us to that oxidation level concept you mentioned. How does that help connect these different groups?
Ah, yes. This is a really neat way to organize functional groups and start thinking about transformations, specifically oxidation and reduction reactions, which are fundamental in organic chemistry. Basically, we group functional groups based on the number of bonds a particular carbon atom has to heteroatoms. Remember, heteroatoms are just atoms other than C or H, so typically O, N, halogens.
Okay. Number of bonds to non-carbon hydrogen atoms.
Exactly. At the bottom, you have the alkane oxidation level. Here, the carbon has 0 bonds to heteroatoms. Think methane or any carbon in a simple alkane chain. One step up is the alcohol oxidation level. This means the carbon has 1 bond to a heteroatom. This includes alcohols, CO, ethers, CO, alkyl halides, CX. Interestingly, we often group alkenes here too because you can make them from alcohols without formal oxidation or reduction, just elimination.
Okay, 1 bond to ONX.
Then comes the aldehyde oxidation level, with 2 bonds from the carbon to heteroatoms. This covers aldehydes, CO counts as 2 bonds to O ketones, CO again, and also things like acetyls, where a carbon has 2 single bonds to oxygen atoms, or even dichloromethane, CH2Cl2, where carbon has 2 bonds to chlorine.
Bonds, makes sense.
Next, the carboxylic acid oxidation level signifies 3 bonds to heteroatoms. This is where carboxylic acid, CO and COH, count as 3, esters, COCO or amides, COCN, nitriles, COANS is 3, and acyl chloride, COCCO, all fit.
3 bonds. Okay, I see the pattern.
And finally, the carbon dioxide oxidation level, with 4 bonds to heteroatoms. This includes CO2 itself, 2 CO bonds, carbon tetrachloride, CCl4, and things like carbonates.
So grouping them like this, it helps you see how you might convert one to another, like going up or down the ladder.
Yeah, precisely. Oxidation generally moves you up this ladder, e.g. alcohol to aldehyde to carboxylic acid, while reduction moves you down. It provides a framework for understanding transformations and planning synthetic routes. It's a powerful way to see deeper connections between functional groups that might look quite different on the surface.
It really does add another layer of understanding. Okay, we know how to draw them. We know the building blocks and functional groups. We can even classify them by oxidation level. What about actually naming these things? There seem to be different kinds of names flying around.
Nomenclature. Yeah, it can seem a bit chaotic. Broadly, you have 2 main types of names. There are trivial names, which are often historical, maybe based on where the compound was first found, like palytoxin from a coral or muscone from musk deer. They're often simple and easy to remember for common stuff.
Like acetic acid for vinegar acid.
Exactly. But with millions of known compounds, you can't have a unique trivial name for everything. That's where systematic nomenclature comes in. Primarily the rules set out by IUPAC, the International Union of Pure and Applied Chemistry.
The official rules.
Right. The idea is that every compound should have a unique, unambiguous name that you can deduce directly from its structure, and you should be able to draw the structure if you're given the systematic name. These names describe the hydrocarbon framework, identify the functional groups, and use numbers to say exactly where everything is attached. Like propan-1-ol tells you it's a 3-carbon chain, propan, it's an alcohol, and the OH group is on carbon number 1.
Okay, logical, but maybe a bit complex sometimes.
They can get very complex. For simple benzene rings with 2 things attached, though, chemists often use an older, but still systematic and often easier system, ortho, meta, and para. Ortho means the groups are neighbors on the ring, positions 1 and 2. Meta means there's 1 carbon in between 1 and 3. Para means they're directly opposite each other, 1 and 4.
Ortho, meta, para. Like neighbors, 1 house down across the street.
That's a great way to think of it. Much easier than saying 1-2-dimethylbenzene when you can just say orthosilene.
Okay, but here's what I really want to know. What do chemists actually call compounds day to day in the lab or when they're talking to each other? Because those long IUPAC names.
Yeah, you're right. Full systematic names for anything moderately complex are just too clumsy for everyday conversation or even writing in the main text of a paper. So what really happens, first and foremost? The supremacy of the structural diagram. A clear drawing is almost always better than any name. The best practice is always give a diagram alongside a name unless it's something incredibly simple and unambiguous like ethanol or acetone. Draw first, name second.
Diagrams rule. Okay. What about names then?
For really common, simple compounds, trivial names are absolutely standard out of habit. Acetone, ethyl acetate, toluene, phenol, acetaldehyde, acetic acid, formic acid, benzene, pyridine, aniline. Chemists use these names constantly without thinking twice.
The old familiar names stick around.
They do. Then there are names for specific mechanistically important fragments. Knowing vinyl versus allyl is crucial. A vinyl group is attached directly to a double bond carbon, CCX. An allyl group is attached to the carbon next to the double bond, CCCX. They have totally different reactivity, which is key for understanding reaction pathways.
Subtle but important difference.
Very important. Same with phenol, pH versus benzyl, BN. Phenol means attached directly to the benzene ring. Benzyl means attached to a CH2 group, which is then attached to the ring. Again, completely different reactivity. PHCl is very unreactive. BnCl is quite reactive.
Got it. pH direct, BNL, one step away.
Exactly. Now, for those really complex natural products, strychnine, penicillin, vitamin B12, palytoxin, nobody uses systematic names. They're impossibly long and unwieldy. They're always referred to by their common, trivial names, usually alongside a diagram in publications. Same goes for amino acids, always alanine, leucine, etc., never the systematic name.
Okay, so common names for the really complex stuff, too.
And then there are acronyms. Labs run on acronyms for common solvents and reagents. THF for tetrahydrofuran, DMF for dimethylformamide, DMSO for dimethyl sulfoxide, reagents like LDA, dibol, PCC, dead. You just learn them. It's essential shorthand.
So when do chemists actually use those systematic IUPAC names?
They're mostly used for moderately simple compounds, maybe with 5 to 20 carbons, chains, or rings where there isn't a common trivial name. Something like non-2-enol, a 9-carbonaldehyde, or cycloocta-1,4,12-diane, an 8-membered ring with 2 double bonds. The names might be a bit long, but they precisely describe the structure, which is vital for clear communication when no simpler name exists.
And for brand new compounds from research?
For new compounds, in the main text of a research paper, chemists will almost always give it a simple tag name, like the yellow ketone, or more formally, compound 5 or amine 12B, and crucially, they'll show the structure right there. The full painstaking IUPAC name is usually buried in the experimental section at the end, more for the official record than for easy reading.
That makes so much practical sense.
It does. So, the take-home advice on naming. Draw the structure first, always. Learn the names of the functional groups cold that tells you about reactivity. Know the common trivial names for the everyday simple molecules. Use tag names with diagrams for complex or new things in discussion. Understand the principles of IUPAC so you can decipher a name if you need to, especially for those medium-sized molecules. And maybe keep a little notebook for acronyms and structures you encounter. The absolute key is never just skip over a name without knowing the structure it represents.
What an absolutely fantastic deep dive. We've really covered the foundations here, drawing molecules economically and realistically, understand the framework versus the all-important functional groups, and then navigating the sometimes tricky world of naming them. It truly feels like learning the grammar of chemistry, and getting this right, this structural literacy, as you called it, seems absolutely essential for everything that comes next, understanding mechanisms, predicting reactions, figuring out stereochemistry, even starting to think backwards with retrosynthesis.
Absolutely. If we connect this to the bigger picture, understanding how molecules are built and named isn't just an identification exercise. It is the absolutely critical first step to predicting how they'll behave, how they'll react, transform, interact with other molecules, whether in a flask or in a living cell. This structural fluency is what empowers chemists to understand everything from, yes, the most potent toxins to the most beneficial life-saving drugs. It's the foundation for designing new materials, new catalysts, new medicines. It all starts with understanding the architecture.
Well, continue to dive deep with us as we keep unraveling the intricate world of chemistry, one concept at a time. Thinking about all this, what stands out to you about how chemists communicate these incredibly complex ideas? Keep those thoughts and questions coming. And as always, thank you for being part of the Last Minute Lecture family.